Hi everybody. The purpose of this video is to go over section 3 of chapter 7, and we are going to introduce to you the sum and difference identities of trigonomic functions. In this video, we will present the sum and difference identities for the cosine. We will talk about cofunction identities and how to apply them, and then we will move on to the sum and difference identities for sine and tangent, and we will talk about how to use these techniques to verify other trigonomic identities. Okay, well, the first thing I want to mention is that, well, essentially cosine or sine, they are not linear functions. As a consequence, since they are not linear, we cannot say that the cosine of a minus b is going to be equal to the cosine of a minus the cosine of b. And we can show this with a very trivial counterexample. Let's let a be equal to pi over 2 and b be equal to 0. Then cosine of a minus b is the cosine of pi over 2 minus 0, which is the cosine of pi over 2, which is 0. However, the cosine of a minus the cosine of b, that's going to be the cosine of pi over 2 minus the cosine of 0. Cosine of pi over 2 is 0. Cosine of 0 is 1, so that becomes 0 minus 1, which is negative 1, and they are not the same. However, it turns out that the cosine of a minus b is equal to this. It is actually equal to the product of cosine a and cosine b plus the product of sine a and sine b. And then from this, we can very easily show that the cosine of a plus b is the cosine of the product of the cosine a and cosine b minus the product of sine a and sine b. And how can we do that? Well, notice that I can write the cosine of the sum of a and b as cosine a minus cosine of negative b, or negative b. So we will have cosine a minus negative b. And then I can go ahead and apply this identity. And if I do, I will have cosine of a times the cosine of b, negative b, minus or plus the sine of a times the sine of negative b. Okay, well, cosine is an even function, and cosine of negative b is going to be equal to the cosine of b. So this becomes cosine a times cosine b. However, sine is an odd function, so sine of negative b is going to be equal to negative sine of b, and this becomes sine of a times sine of b, with a negative sign right here. So that's how they come about. Now we're going to use these functions or these identities to come up with exact value for trig functions for angles that we haven't done yet. Thus far, we have figured out exact values for sine and cosine for all of these angles, 30, 45, 60, and there are versions in all the other quadrants. However, we haven't done 15. We haven't done 75. We haven't done 105 or 165 or 345. And then there are a few others here that we haven't done. However, with the sum and difference identities, we can actually come up with exact values for many of these angles. Now, for doing this in terms of degrees is pretty straightforward. Doing them in terms of radians is kind of tricky because remember, if 30 is pi over 6, then 15 is going to be pi over 12. So a lot of these, when converted to radians, will have a 12 in the denominator. So it will be useful if we actually have equivalent forms for various radian measures where the denominator happens to be 12. And here's what we have. These are all of our equivalent forms. And we can actually use these tables as guides to come up with combinations of angles so that we can actually compute exact angles using the sum formulas and the difference formulas. Okay, and here's our first problem. Here we want to compute the cosine of negative 75 degrees. Well, how could we do that? Well, we could write this as the cosine of 45 degrees minus 120 degrees. That would give us negative 75. Okay, cool. Let's do that. Well, this right here, we would need to use our difference identity, and the difference identity in this case is going to be the cosine of 45 times the cosine of 120 plus the sine of 45 times the sine of 120. Okay, well the cosine of 45 is the square root of 2 over 2. The cosine of 120 is negative 1/2. Plus, and once again, the sine of 45 is negative root 2 over 2. And the sine of 120 is going to be equal to the square root of 3 over 2. Okay, we can multiply and simplify, and we will have negative root 2 over 4 plus root 6 over 4, and further simplifying it, making it look a little neater, we can write this as root 6 minus root 2 divided by 4. And that is the exact value for the cosine of negative 75. Now, what about the cosine of 17 pi over 12? Well, we can go back to our table of equivalent forms, and what you will see is that we can rewrite that as the cosine of 9 pi over 12 plus 8 pi over 12. 9 pi plus 8 pi is 17 pi. And once you've done that, you can go ahead and use our sum identity, which will be the cosine of 9 pi over 12. Well, actually, first, before we do that, let's do this. Before we do that, let's actually go ahead and simplify the fractions here, now that we've got the addition part right down. And 9 pi over 12, we can write as 3 pi over 4 plus, and then 8 pi over 12 we can write as 2 pi over 3 because that has a common factor of 4. Now we can apply the identity, and that will be cosine of 3 pi over 4 times cosine of 2 pi over 3 minus sine of 3 pi over 4 times sine of 2 pi over 3. Okay, well, the cosine of 3 pi over 4, that actually is the cosine of 45 in the second quadrant. So this is going to be negative root 2 over 2. The cosine of 2 pi over 3 is, oh, I forgot the negative sign there. The cosine of 2 pi over 3 is negative 1/2. Minus the sine of 3 pi over 4 is also negative root 2 over 2, but it's going to be positive since we're in the second quadrant. And the sine of 2 pi over 3 is going to be equal to the square root of 3 over 2, once again positive because we are in the second quadrant. Okay, well, negative root 2 times negative 1, that's just positive root 2 over 4 minus square root of 2 times the square root of 3, that's the square root of 6 divided by 4, and that will give us root 2 minus root 6 divided by 4. And this brings us down to this problem right here. Now notice that this is the identity for cosine A minus cosine B. So this right here is going to be equal to the cosine of 173 minus 83. Turns out that 173 minus 83 is 90, so this is going to be the cosine of 90 degrees. I forgot that little detail. Let's put a degree symbol there and there. And of course, the cosine of 90 degrees is 0. And there you go. That's it. That's how we do those problems. Now, let's talk about the cofunction identities. And we've actually seen these before, because we talked about these when we talked about section 5.2, when we introduced the right triangle perspective of trig functions. And we noticed that the cofunction of sine is cosine. The cofunction of tangent is cotangent. And the cofunction of secant is cosecant. And what does that mean? Well, that basically means that the sine of theta is going to be equal to the cosine of its complement. The cosine of theta is equal to the sine of its complement. The cotangent of theta is equal to the tangent of complement, and then the other three fall out as well. And of course, we can express this in radian form, and we can express this in degree form in your notes. And this gives rise to a number of problems that we can play with. And here's the first one. And this one is pretty much just following the examples. Here we want to write secant in terms of its cofunction. And the cofunction of cosecant is secant. Okay? And we want to write this as the cofunction of a complementary angle. So the complement of 5 pi over 24 is going to be pi over 2 minus 5 pi over 24. All right, and we can just do a little work on this. This will be equal to secant of 12 pi over 24 minus 5 pi over 24, which will give us the secant of 7 pi over 24. And there you are. Okay, now you'll see a couple of problems like this. And here we want to use the identities and enter in the appropriate trig function name. And now notice here we have the tangent of 67. Well, the tangent of 67 is going to be equal to the cofunction of its complement. So the tangent of 67 is going to be equal to the cofunction, which is cotangent, of its complement, which will be 90 minus 67, or the cotangent of 23 degrees. We have something in the denominator here, so we need to use the reciprocal identity, and the reciprocal of cotangent is tangent. So this will be equal to 1 over tangent of 23. And what does that tell us? That means we want to put in tangent down here. Okay, we have a few other problems that we can work with. The first one and the next one is this. Here we want to use the cofunction identities to find the quadrant 1 angle that satisfies the following statement. The cotangent of theta is equal to tangent of 3 theta plus 54. Okay, now remember, the cotangent of theta will always be equal to its cofunction, which is tangent, evaluated at its complement, which will be 90 degrees minus theta. And of course, that will have to be equal to tangent of 3 theta over plus 54 degrees. Well, it turns out that in quadrant 1, tangent's a 1-to-1 angle, is a 1-to-1 function. As a consequence, for this to be equal, that would require that 90 degrees minus theta is equal to 30 degrees, or 3 theta, plus 54. Okay, so cool. We can add theta to both sides. We can subtract 54 from both sides. And if we do, these cancel, we are left with 36 degrees is equal to 4 theta. Okay, cool. And that would mean that theta is equal to 36 divided by 4, or 9 degrees, which of course is indeed in quadrant 1. And then for this one, we want to solve this statement for theta. Well, once again, the cofunction of cosecant is secant. And the cosecant of theta is going to be equal to the secant of its complement, which will be pi over 2 minus theta. And that has to be equal to the secant of 2 pi over 3. Okay, so if this is going for these two to be equal, we actually have to have that pi over 2 minus theta is equal to 2 pi over 3. And that would imply that theta is equal to pi over 2 minus 2 pi over 3. And that will be equal to, for getting a common denominator, 3 pi divided by 6 minus 4 pi divided by 6, which will be equal to negative pi over 6. So we have here that theta is equal to negative pi over 6. Now we want to talk about the sum and difference identities for both sine and tangent. And these are the sum and difference identities for sine, and these are the sum and difference identities for tangent. Once again, we're not going to derive them, we're just going to state them, and we're going to talk about how to use them. Of course, the one thing that you can notice is that if you start off with the sine of a plus b, which is sine a cosine b plus cosine a sine b, then sine a minus sine b we can write as the sine of a plus negative b, and of course that will give us sine a times cosine of negative b plus cosine of a times sine of negative b. Once again, since cosine is even, this is nothing more than sine a cosine of b. And here, since sine is odd, we have a negative cosine a sine of b. But let's go through a few examples and see how these things are used. Okay, first we want to find the sine of negative 15 degrees. So what we need to do or find two angles which we already know the exact values for, which will sum to negative 15. And the two that come to my mind are the sine of 30 degrees minus the sine of 45 degrees. That will give us negative 15. And now we can use our difference identity, and that will be the sine of 30 times the cosine of 45 minus the cosine of 30 times the sine of 45. And those we know the values for. The sine of 30 is 1/2. The cosine of 45 is the square root of 2 over 2. Minus the cosine of 30 is going to be the square root of 3 over 2. And then the cosine of, or the sine of 45 is going to be root 2 over 2. And that will give us the square root of 2 minus the square root of 6, all of that over 4. What about tangent of 13 pi over 12? Well, we can write this as the tangent of 4 pi over 12 plus 9 pi over 12. Using the identity that we have for tangent, this will be equal to the tangent of 4 pi over 12 plus the tangent of 9 pi over 12 all divided by 1 minus the tangent of the products, or the product of the tangents. Tangent 4 pi over 12, there should be a 2 here, times tangent 9 pi over 12. Okay, well, tangent of 4 pi over 12, that is the tangent of pi over 3. the tangent of 9 pi over 12 is going to be plus the tangent of 3 pi over 4. And then over here we have 1 minus the tangent of pi over 3 times the tangent of 3 pi over 4. Okay, now we can actually substitute in some values. The tangent of pi over 3 is going to be equal to the square root of 3. The tangent of 3 pi over 4, well, that's just negative. That's just minus 1 because we're in quadrant 2. That's 45 degrees in quadrant 2. That's minus 1. And then that is going to be divided by 1 plus minus the square root of 3 times negative 1 for 3 pi over 4, which will give me plus 1. I forgot the a in over here. Okay, now to deal with this, we would need to multiply both top and bottom by the conjugate of this, or more specifically, 1 minus the square root of 3. And we're going to do that for the denominator. We've got to do the exact same thing for the numerator, 1 minus root 3. And then what we will have on the denominator will be 1 minus 3. And then up here we will have first the square root of 3, outer minus 3, inner minus 1, and then last the square root of 3. Simplifying, we will have, well, there should be a plus there. Root 3 plus root 3, that's 2, the square root of 3, minus 4, all over negative 2. And we have a common factor of negative 2 here, so we can get rid of that. And then that will give us 2 minus the square root of 3. And there you go. That will be our answer. Now, if you look at this one over here, you'll notice that this is the formula for the tangent of 100 degrees minus 70 degrees. This is actually the difference angle formula, which of course is going to be equal to the tangent of 30 degrees, which is equal to 1 divided by the square root of 3. And if we rationalize this, we will have the square root of 3 divided by 3, which is what we're looking for. Okay, we have 3 more examples to go over, and the next one is this one here. We want to write this expression as a function that has only theta as an argument. Now, if you notice, this is basically the sum of 2 angles, so we can use the sum identity for sine. And if we do, we will have sine of 120 times the cosine of theta, and that will be plus the cosine of 120 times the sine of theta. And of course 120 is in the second quadrant, and the sine of 120 is the square root of 3 over 2. We'll multiply that by the cosine of theta. Now, since we're in quadrant 2, the cosine is going to be negative, and the cosine of 120 is going to be negative 1/2, so we have minus 1/2 times the sine of theta. And that would be the answer for that particular problem. Now here, we have that cosine of A is negative 7/25, and A is in quadrant 3, and sine of B is negative 3/5, and B is in quadrant 4. And we want to find the sine of A minus B. Well, using our difference identity, we know this is going to be equal to the sine of A times the cosine of B minus the cosine of A times the sine of B. Okay, well, we know what cosine of A is, we know what sine of B is, but we don't know what these two are. But we do have the Pythagorean identities. So we do know that the sine squared of A is going to be equal to 1 minus the cosine squared of B. And of course, the cosine squared of, cosine squared of A, that doesn't make much sense. The cosine squared of A is going to be negative 7 squared divided by 25 squared, which will be 49 divided by 625. So we probably want to make 1 be equal to 625 over 625. And if we do, we will have that the sine squared of A is equal to 576 divided by 625. All right, so with that, we can compute the sine of A. The sine of A is going to be equal to the square root of this. However, we are in the third quadrant, and when we're in quadrant 3, the sine of A is going to be negative, so we need to take the negative square root, and if we evaluate this, we will have negative 24 divided by 25, because the square root of 576 is 24, and the square root of 625 is 25. So now we have now we have sine A. It's right there. We still need to figure out what the cosine of B is. Well, we can use the exact same approach. Cosine squared of B is going to be equal to 1 minus sine squared of B. And we can write this as 25 over 25 minus 9 over 25. And that will give us that the cosine squared of B is equal to 16 over 25. Okay, so then the cosine of B is going to be equal to the square root of 16 over 25. Furthermore, since B is in quadrant 4, cosine is going to be positive, so we'll have a positive square root. If B is in quadrant 4, cosine of B will be greater than 0, and if A is in quadrant 3, sine of A will be less than 0. Okay, so evaluating this, we will have that the cosine of B is equal to 4/5. So we have the sine of A, it's right here. We have the cosine of B, it's right here, so we can figure the rest of this out. This will be equal to negative 24 25ths, negative 24 over 25 times 4/5 minus cosine of A is negative 7/25, and then sine negative, I forgot the negative there, and then sine of B is negative 3/5. All right, so negative 24 times 4, that is negative 96, divided by 25 times 5, which is 125, and then minus negative 7 times negative 3 is positive 21, once again over 125, and then when we put those together, we will have negative 117 divided by 125. So this is the angle of sine of, this is the value sine of A minus beta. All right, now suppose for the next part we have, suppose that the tangent of A minus B is negative 177 divided by 44. We want to know the quadrant of A minus B. Well, if the tangent of A minus B is this, that tells us that A minus B is going to either be in quadrant 2 or quadrant 4. Those are the only two quadrants we can have a negative tangent. Now notice here that sine is less than 0. Okay, so since sine is less than 0, since sine of A minus B is negative, we know that this can either be at quadrant 3 or quadrant 4. The only quadrant where sine can be negative and tangent can be negative is, of course, quadrant 4. Because that's both, that quadrant satisfies both conditions, so the quadrant will be quadrant 4. Okay, the last example we have is to verify identities. And you'll see a few of these in your homework, but primarily the idea is that they'll give you an identity and they'll ask you to verify it, but they'll walk you through it, so that way they'll at least give you a strategy for verifying it. And here, the strategy for verifying it is the fact, in this particular case, is the fact that this is a this is the sum of two angles. This is the sum of two angles. So we're going to be using our sum identities. And so the sum identity for sine is going to be sine of the first angle, which is 7 pi over 6, times the cosine of the second angle, plus the cosine of the first angle, 7 pi over 6, times the sine of the second angle, minus, and then the cosine, the identity for the cosine of the sum of two angles is going to be the cosine of the first angle, which is 2 pi over 3, times the cosine of the second angle, minus the sine of the first angle, times the sine of the second angle. And all this theoretically should be equal to 0. Okay, well, let's see what we got. Well, it turns out that the sine of 7 pi over 6 is negative 1/2. So we have negative 1/2 times the cosine of x. If the sine of negative of 7 pi over 6 is negative 1/2, then the cosine of 7 pi over 6 is going to be equal to negative root 3 over 2, because this is in quadrant 3. So negative root 3 over 2 times the sine of x. Minus, okay, this should be 2 pi over 3, not 2 pi over 2. Okay, well, the cosine of 2 pi over 3 is going to be equal to negative 1/2. It's actually 1/2, but since we're in quadrant 2, it'll be negative 1/2 times the cosine of x. And then the sine of 2 pi over 3 is going to be positive root 3 over 2. So we have minus root 3 divided by 2 times the sine of x. Okay, we can distribute, and if we do, we will have negative 1/2 cosine of x minus root 3 over 2 sine of x plus 1/2 cosine x plus root 3 over 2 sine of x. And notice that we have some cancellations. This cancels with that, this cancels with that, and we indeed have 0. And that is all that I have for this particular video and this particular section. If you have any questions, please come reach out to me and I will help you in any way that I can. And this is Bob Boyle, signing off.